Okay, so we can continue our discussion about physics beyond the standard model, and as I promised, we will take one example of possible extension of standard model according to the outline. We covered the first part, which was the evidence and the possible extension of standard model, and now we will focus on one example. And from the extension, there was about 9 different directions for beyond the standard model. So, what do you think? Which direction I will take it right now? Susie. No, not Susie. Although Susie for me, but Susie is too advanced for the. Also, here is a community of gravity, so I decided to have the extra dimension extension as a model of beyond the standard model to also make it some interesting to our colleagues here as well. So the extension of extra dimensions as a windows for physics beyond the standard model will cover this. I will explain to you why extra dimensions, and then the history of extra dimensions started from Kaluza-Klein theory. Then we jump to 1990 or so about large extra dimension, which is known as Arkan-Hamidi modulus Trivali, ADD model, and then work with extra dimensions. Don't worry, simple things. We'll discuss it now. Work with extra dimension. This is Randall Sondrum, RS model, and then we'll discuss collider signature. Can you imagine that there will be collider signatures for all of this? But we will see now. Why extra dimensions? The easy answer, why not? First of all, we didn't study gravity yet, or general relativity yet. Adil just start with a special theory of relativity, but you will see that general relativity is in 4-dimension framework. In fact, it's in 4 dimension because we choose to make the dimension 4. But in principle, general theory of relativity can be valid for any dimension. Any dimension, okay? So 4 dimension is not, any special about the 4, except that we are familiar with. Now, there's a lot of possible extensions of spatial dimension beyond the 3, because the 4 is 1 plus 3 is essentially. And as I told you, several trials to study the general relativity on extra dimensions. Back to the Kaluza-Klein theory in 1920. And in fact, this theory is not just simple exercise. Let us do general relativity in 5 dimensions instead of 4. He was, especially Klein, Kaluza in the beginning, he was trying to study gravity in 5 dimensions and show you that this 5-dimension gravity will be seen from the 4-dimensional point of view as a 4-dimension gravity plus extra force, which is electromagnetism. And therefore, he was dreaming to unify gravity with electromagnetic force, electromagnetism, in one theory. This theory is really gravity in 5 dimensions. You will see that really when we go to higher dimensions, we will have more freedom to include extra interaction and extra force. And this is the idea of even string theory. String theory is in 11 dimension or 10 dimension. And this 10 dimensions, in fact, help the theory to have not only gravity in 4 dimension, but also standard model, the SU3 cross SU2 cross 1 that I'm talking about, and even extra, fifth force or some other extra forces, because you are enlarging the theory and you will see that degrees of freedom becomes much more than the standard model alone. So extra dimension aims to unify the fundamental forces, as we will see, and in fact, we will in string theory or in theories with extra dimension, with the direction of the unification over extra dimension, the gravity will be the unified field theory, and then at lower scale and lower dimensions where some extra dimension will disappear and the compactification and all these terminologies that we will discuss, you will see that we have 4 dimension gravity plus extra forces. So you see that gravity maybe is fundamental and the underlying theory of everything. Okay, string theory is enough, as I mentioned. Also, recently in 1990, ADD or Rundle syndrome, they were also aiming to solve the hierarchy problem. If you remember the hierarchy problem I mentioned for the one loop corrections of the Higgs mass that I mentioned in the previous lecture, SUSY is very nice, offers nice solution that it offer partners for the particles, so that we will have two loops, not just one loop, and the sum of the two loops cancel each other. One was Fermi and give you minus sign, one was scalars which give you plus sign, and the sum cancel each other, and the hierarchy problem disappear. Extra dimension is solving the hierarchy problem in another way, and we will discuss now if they succeed or not in solving the hierarchy problem in extra dimension. Yes?
So extra dimension means you go to a higher energy scale.
No. You can have higher energy scale in 4 dimension. In the LHC,
but you will not find like find theory for all this.
Just a second. Higher energy scale can be done in 4 dimension. You can have as energy as you want in 4 dimension. Black holes, early universe, and early. No, here is the 4 dimension will be extended to, maybe in my example today is 5. So 4 plus 1 could be more as a string theory, 10 dimensions. So the space-time itself is extended to higher dimensions. Energy is something else. We are talking about the space-time, and then in the space-time, whatever energy you have, the universe you have, cooling down, and so on, the procedure will be as normal, but with different dimensions. Please come. No.
Like in LHC, you increase the energy, so you go to GOT and 2. So
you go to what?
GOT and 2.
And
2. Theory of
everything. String theory?
Theory of everything.
Okay.
So you increase the energy. Like string theory, you want to increase the dimension?
No, string theory to be consistent in 10 dimension and 11 dimension. You know, if you go in higher energy at LHC, you get some effective theory from the higher dimensional theory. So what you have seen from GOT or from string theory at LHC is just effective. Is remnant effect that you may be probing at low energy. We call it low energy effect. Okay, but the theory itself as a fundamental theory will be built in 10 dimensions. Okay?
Just wanted to ask that if we assume there are more dimensions that are unobserved, because we can only observe 3 special dimensions.
We will see now the procedure to make it unobserved. This is the issue that Einstein raised when Kaluza wrote the paper in the time of Einstein, and the paper went to Einstein to review, and he kept it with him 2 years, not published, because he was happy, as I understand, he was happy with the idea of the unification between electromagnetism and the general relativity. However, he was asking about the X dimension, how we can prevent the gravity to propagate in extra dimension, and then we change the Bohr law and the Newton's law, and this is unacceptable. Until Klein came and he made what I will tell you about it. He made some nice trick to make the extra dimension wrapped in very small radii, and make its effect negligible, so the theory will effectively looks like 4 dimensions.
I think that's maybe what he meant by being at very high energy, because small scale at the LHC means very high energy.
Yeah, you can probe. If you can probe it, you need high energy to probe extra dimension. Okay. But this is if it is a small extra dimension. You will see that we may have large extra dimension as well. Okay, so extra dimension also can be motivated by explaining cosmological inflations, maybe dark matter, and also play a role in dark energy. Okay, so now general relativity in 5 dimensions. This is Kaluza paper essentially. So in 5 dimension, Adil didn't try to do the metric, but next time he will write the metric ds squared g mu nu dx nu and the mu 0, 1, 2, 3. Now when I have extra dimension, nothing will change except the metric will be more general, g m n dx and dxn, and m from 0 to 4, 0, 1 to 5 dimension. And then Kaluza, in fact, tried to simplify things. So he takes this 5 dimension metric. He wanted to have the gravity of the 4 dimension in the metric. So he thought that the factor, the decomposition of the 5 dimension metric will contain a 4 by 4 metric, which will be the original Einstein metric, and then 4 times 4 by 4. 4 times 1, which is row here, and the column, this is row, and this is, which is row, which column is this is 4, and this is 4. 1 times 4, 4 times 1, and this 1 times 1. So we make the decomposition of the 5 times 5 metric. In this metric, 5 times 5, I don't know what that. Should I cancel? Check it? Okay. So the metric in 5 dimension will contain the following. Metric in 4 dimension, g mu nu, some vector field a mu, and some scalar field phi. So in fact, if you count the degrees of freedom, because in 5 dimension, the GMN is essentially symmetric, 5 by 5, it's about 15 degrees of freedom. G mu nu is 10, and this is 4 plus 1, so again, degrees of freedom 15. Okay? So in this decomposition, you have the 4 G mu nu and 4 dimension G mu nu, you have 4 vector a mu and scalar field phi. So the vector a mu, Kaluza was trying to use the a mu as electromagnetic field, the 4 vector potential of the electromagnetic field. The scalar field phi is very useful, and in string theory, it has explanation. It's called the Delaton field, and they make relation with coupling. But in Kaluza models, he kept it equal 1, in fact. Okay, so he take phi squared to be minus 1, just to make the theory focus on the G mu nu and the A mu. And in fact, to write this part in the most general form, you know, the metric could be second rank tensor, G mu nu, but also can be linear combination of vector times vector, vector times. So he wrote it in this way. So the 4 by this part, the 4 dimensional block here, could be G mu nu minus A mu, A mu. This is the A mu, and this is the transverse, and this is taken to 1. So he worked out the 5-dimensional metric as a 4-dimension plus vector field. And then he derived the field equation. You know how to derive field equation? Like in the general relativity, I will show you sometimes that you use the Einstein-Hilbert action, which can be obtained from the metric, and then you work out the field equation. The field equation in Einstein, you get G mu nu, the 4-dimension Einstein tensor G mu nu delta equal to the energy momentum tensor T mu nu as normal. Okay? And then you get extra equations when you make the variation, or Euler-Dirichlet equation. You make the variation for the extra degrees of freedom, A mu. You get also another equation, Nabla squared, F mu nu equals 0. Okay? This is remind you with what? What? F mu nu Nabla squared. This is Maxwell's. This is part of Maxwell's equation. Okay, and in fact, the T mu nu, if you count, if you check T mu nu, you will find that T mu nu is given in terms of the vector field A mu in this form. So this means the A mu can be source A mu of this decomposition, which is 4 times 1 component, can be source of the gravity, while the electromagnetism is a free. There is no source. The gravity doesn't really generate current. Yes.
The stress momentum tensor
Yes.
is the ordinary the ordinary stress momentum stress tensor has the general relativity in 4 dimensions.
Yes, but here we don't have matter source. Here it is coming from the connection with the mu. For that reason, I'm giving you the expression. But it appears in the right-hand side, so it plays the role of the usual energy momentum tensor. For that reason, I'm saying the vector field, the a mu, the f mu nu, playing the role of the source of the g mu nu, of the energy of the gravity. While this field, Maxwell's field, in Maxwell's equation of this field has no current, has no source, is zero. So the field a mu play the role of the source of the gravity, while the g mu nu doesn't really play the role of any source of the electromagnetism.
But my question is, G mu nu is five dimensional.
No, if I am using mu nu, then it's 4. 5 m capital M capital M.
Okay. So
This is 4 dimensions. This is no. This is Einstein.
okay, this is Einstein
Yes.
field equation. What is the difference between this? يعني Kaluza with drive the same equation, right? This
with a specific energy momentum tensor, which is given like this. Now, Galuza is not working in the sky. He has a 5 dimension, and he wants part of the 5 dimension to give you the Einstein 4 dimension plus extra. So he got Einstein
okay.
plus Maxwell. Okay.
يعني الجزء اللي تحت هو المعادله اللي تحت هي الاكسترا الشغل الزياده بتاعت نيوتن.
And this T mu nu also extra because it is defined in terms of the A which appeared in the metric. So it is self-contained.
Maybe it's better if you just write Einstein field equations in the 5 dimension, which is
G capital M equals
is
0 is 0. There is no source in the 5 dimension. Instead of G capital, I think I wrote it somewhere, but if you take this and work, you get G Mn equals 0. And then you extract the 4 dimension component from this general equation, you get this 2. Okay? So I hope I convinced you that Karusak line in 5 dimension goes to GR and Maxwell. This was convinced to Einstein as well, but as I told you, he was worried about the extra dimension, how we can handle the large extra dimension, how we forbid the non-conservation of the physical quantity from going to extra dimension, and then we will not have any control. Until Oscar Klein came, and he suggested what's called now compactification. Okay, so this is now, he take the 5th dimension, he said if I have kind of 5th dimension, which is x4 for example, in fact it should be wrapped, this is very simple example to have the extra dimension wrapped around circle for example. So x4 should be identified with x4 plus 2 pi r. The radius of the circle is r, so this point will be identical to the point when you go around the circle with 2 pi r. So if in this case, what will happen? If I have any function, metric or the vector field or whatever, function of the 4-dimensional coordinates and the 5th dimension, this should not be changed. Single valued function, so x4 change it to x4 plus 2 pi r, it should give me the same result. And this is what is known as compactification. And in fact, you can write this, you can make expansion for this any function of x mu x4 with Taylor expansion or whatever, and then to keep x4 is invariant under this.
Fourier, I think, right?
Sorry?
You expanded in terms because of
This is what I'm saying, but before we got n dot y is x4, in fact you have b dot x in general, and the y is invariant under 2 pi r, so the b in front of this should really be kind of discrete, and this will be n over r, so that y, when y goes to 2 pi r, and this is n over r, r cancel with r, and the n times 2 pi give you 1. Yes?
Is there a connection between the compactification here and the typological definition of the compactification?
What is the topological definition
لو
of
في حاجة اسمها compactification of a topological space ده ملوش معنى.
I think في علاقة، بس يعني احنا هنا we are taking very simple زي ما بعمل كده بالنسبة ل x4 انها to be rotated around the x dimension ده around some circle so that you get rid of the of this as mode for this coordinates. So you will have the metric g mu nu which depend on x and y as a g mu nu, but now you have modes, so you have n run from minus infinity to infinity g mu nu n of x times this exponential. All fields, scalar, vector, whatever, can be also expanded in the same way. This is where you said that we have now infinite modes because this rotations will make this momentum, which was continuous, to be discrete and defined with n over r. Yes?
So in here is integral.
Integer, yes.
So like a quantized compactification.
Yes. Yes.
Application.
Yes, yes. You usually, you know, if I wanted to make this before I make any compactification, I will have e to I by dot y. But since y changed by 2 by r, by should also absorb this 2 by, so it has to be n over r for that reason.
So like
To be single valued problem.
like quantized, like quantum or
Quantized here means it has an integers, like in quantum mechanics when we have hydrogen spectrum, we have integer n dependence on the spectrum. You remember?
so there is a link between this and the quantum mechanics.
No. Just quantized here means it is depends on the integer n. A jump before.
It's easier to call it Fourier modes because this exponential you can describe it in cosine and sines, and this is a compact, or this is a finite interval function. So you can really always write it in sines and cosines.
Okay. So this is the idea of compactification, that you make the x dimension curved around some shape like cylinder or circle, and then you have this modes, and this modes allows you now to have this type of equation. So the Einstein field equation, in fact, now you can write it in as a partial mu minus partial y, in the fifth dimension. Instead of the box of the five dimension, you have the 4 plus. And because g mu nu of y has now exponential e to I n over r, y will have a derivative over the y and bring the n square over r square, and this will give you this
But
equation.
this is the linearized equation. Right?
This is field
the
equation.
linearized.
We didn't linearize it yet. This is a g mu nu of x and y in general.
But then you have to have covariant derivatives acting on G, not just ordinary derivatives. Right?
You mean in the equation g mu nu here?
So this is why it should be the linearized.
Yes, as to have it like wave equations like this. So these wave equations now show that if n equals 0, which is a 0 mode, you will get free massless g mu nu, partial Laplace square g mu nu equals 0. This is a standard wave equation. Now, if you n different from 0, 1 or so, this will give you mass, and this is a higher mode, will have a higher mode of the gravity, of graviton, will be massive. And the mass, the lowest or the second excited states or the first excited states will be 1 over r squared. Also the same for the field a mu. This is the equation of motion, and because it has e to I n over ry will give you the term n square, play the role of the mass, but when n different from 0. So this will be massless, like photon, unless n equal 1 or 2 and so on, it will have a mass. So the excitation, the higher modes of the photon will be massive. Exactly like the graviton. Graviton 0 mode will be massless, higher modes will be massive, and they have the same mass in this scenario. Scalar field is the same story. Klein-Jordan will be partial mu plus, and so on. So the mass of all this higher modes will be mn equal n over r essentially. and n is the mode of excitation. Is it clear like this? Yes.
All of these modes are theoretical, just theoretical, right?
So far, yes. Zero modes is not.
Okay.
Okay. Higher modes is a prediction, not theoretical, but prediction. And to be realistic, you need to drop some of them. Okay, but let me tell you this story, which makes Einstein happy, and he said, okay, no problem with extra dimension. That I think Klein assumed R to be related to the higher scales, which is Planck scale. So take R 1 over m Planck length essentially. And Planck length is very tiny, 10 to minus Planck scale. The energy Planck scale is 10 to 18 GeV, and the Planck length is 10 to minus
23
meter, 10 to minus 18 GeV minus 1 if you want. So this is very tiny, very, very small. No way to probe it or to assume it play any roles. So it becomes like, okay, nice theoretical exercise, and the gravity is obtained as zero mode with this, and also electromagnetism and the scalar field, and there is no big damage that we should worry about. And they also wrote the action of the scalar field. For example, the Delaton I told you, here is the zero mode, which is the important for us, the usual Klein-Jordan, plus extra modes, as you can see, some from 1 to infinity, phi mu, phi n, you have phi 1, phi 2, phi 2, phi n, phi infinity, and their mass term, equal mass term, universal mass term for all these modes. Similar to this, the A, and this is zero mode massless, and then higher modes will have a mass, and the mass splitting is 1 over r squared. Same for the A gauge field or the A nu or electromagnetic field. The action will be as usual 1 over 4 F m n. You expand it, you get the usual F0 mu F0 mu, which is our action for Einstein Maxwell theory, and then you have also extra term which A5. You have partial mu A50, partial mu A50. A50, which is essentially phi, scalar. Okay, so this will be also contains the partial mu phi, partial mu phi. Now you have also higher order with mass n squared over r for a mu n and a mu n. For graviton, you will have the similar story. You have the equation for 5 dimension, partial m gmn minus partial n gmn equals 0, and then you can decompose and you get from the action square root minus gr, similar to what we did before. This is the action of the 4-dimension gravity, square root minus g capital R. This is r hat in 5 dimension, this is r in 4 dimension, and you see in addition to r, you get the zero mode ff mu multiplied by the scalar field phi adding to the r, and this is partial mu phi or phi 0. So this is really the action now in gravity, but gravity coupled with a scalar field and coupled with vector field. Okay? You lost any? So this is very simple. We take just the 5 dimension and decompose it. Yes.
Is the zero moment, is the zero mode n equals 0?
Yes.
Means the mass equals 0.
Yes.
This means that he will describe the electromagnetic field. Yes.
Yes.
So he got gravitational field. Yes.
ايه
Other mode, higher mode.
لا انت عندك زيرو مود for gravity, zero mode of electromagnetism, zero mode for scalar field, and the higher mode for each.
But what I want is the mass is the photon is massless. So mass equals 0 means n equals 0. So it will be described only the electromagnetic field.
Yes.
That's what I understand.
But the others are also photons, but excited photons, which are massive. And I am saying the graviton also, the zero mode is a graviton, which is massless. But there is higher modes for graviton, which are massive.
The last equation, is it like
No, no limit. You take the equation in 5 dimensions. This is Hilbert-Einstein action in 5 dimension, and you write it. And when you calculate the R hat, good luck in some long calculation, you will get this expression.
But sometimes it is called the low energy limit of the field.
But low energy, it looks like you are neglecting or you have approximated. Anyway, there is nothing. You you get the 4 dimension from the 5 dimensions. But as you see, it's not just the square root minus GR, but you get extra terms also belong to this, coupled with the metric minus square root G. So this is the reason why the gravity now is not interacting with the electromagnetic field and scalar field. Yes.
There are actually excited modes for photons. If we assume this, how can we achieve it?
We will come to the detection. The signals for a collider is mainly to discover the higher modes of the photon or the graviton or the scalar field dilaton. The whole game now experimentally is to observe something. We are now in the construction of the theory, and then we will see the drawbacks and the bonus that we received from the theory and so on. Yeah, this is interesting because now if you have this 5 dimension, in fact, you can now discuss whatever we call the Hilbert-Einstein actions. We know in 4 dimension the coefficient is 1 over the Newtonian coupling constant or proportional to Planck squared. If you make matching with a 5 dimension metric, you will find this expression, which is related to the integration over the volume, is given, if you match it, will be given by m Planck square. So the m Planck in 4 dimension, which is an issue for us because m Planck is, you remember in the hierarchy, is 10 to 19 GeV or 18 GeV, and this takes everything to high scale and so on. So now m Planck equal to m star, which is m Planck in the 5th dimension or in higher dimension with power 2 plus n. Remember, n is dimension, n is 1 in the 5th dimension, so it could be m star cubed times the volume. And the volume, if it is large, you know, you could imagine m star, the Planck scale in the higher dimension, could be our Planck scale divided over the volume. And for large volume, you could have m Planck, m star much lower than the Planck scale, which is 10 to 19 or 18 GeV. Therefore, people started to talk about m star of order TV scale only. M Planck in 5 dimension could be just a TV scale because it is really, times a large volume giving you this m Planck in 4 dimension. Remember this because we will discuss it when we try to solve the hierarchy problem. So now, m Planck, when I wrote m Planck, this is our 4 dimension Planck scale, which is 10 to 19. M star is a Planck scale in the higher dimension, which comes with a power different from 2. 2 plus n, and this is the volume. So now for the radius that we take it to order m Planck, the length is 10 to minus 32 centimeter, as Adil said. This will give you large volume, and this gives you m star of n1 or whatever n star. It will be, as I told you, almost 1 TV. There is a possibility to have Planck scale and higher dimension TV scale. So now it comes to the new, not very new because I told you it is 1990 essentially, the idea of large extra dimension. Let us make it large because when you have large extra dimension, you have large volume, and then m star could be quite low. So in large extra dimensions, you could have this setup where we have hyperplane, like this, we call it brane, and in fact we will have this brane is a 4-dimensional, and then 5th dimension, and this bulk is 5 dimension, but like this this wall is 2 dimension, and this wall is 2 dimension, and this is the third, and the whole room is kind of 3 dimension. So this is the idea. They started to divide the universe in this hyperlink or hyper services to say that the standard model is stuck on one of those branes to avoid the problems that the particles or the interactions, electromagnetism and any other interaction goes to the bulk. Only gravity allowed to go to the bulk because gravity, is working in the whole space. And they used this relation to make the extra dimensions not to 10 to minus 32, but rather large. Could be millimeter or could be micrometer. So if in the case of n equal to r will be 100 micrometer. So they have in the setup some extra dimensions. This extra dimension d could be of 2 dimensions. Each of them is 100 micrometers, and the matter field and the interactions is localized in the brain, and this brain is hidden sector brain, and this is the setup of the model of the universe in what we call ADD scenario. No,
This is
ADD, because this is universal propagation. Yes.
Are there any constraints on the number d?
Yes.
Could it be infinite?
Just a second. The R, the number D is not constrained. In fact, they started to have it just 1, so that we can have 4, another 4 plus 1. In fact, if you calculate this expression and you add n to be 1, you will find it that 30 minus 17, about 13. It will be 10 to 13 centimeter. This is give you factor 1. So this is huge. This is, if you take any dimension, the radius of this extra dimension will be 10 to 13 centimeter. This is contradict the astrophysical and solar system and all the constraints. For that reason, the first in this setup, I will show you another setup where you could have 1. But in this setup, you cannot go beyond below 2 dimensions. So with 2, you will have 15 minus 17. This is will be 10 to minus 2, which give you this 100 micrometer. Okay? So you need it at least 2. What about if I take it 3? You will get it much smaller. You know, if you get it 10, like in string theory, you will get it 10 to minus 10 is 3, 10 to minus 14, something like Planck length, like the extra dimension in string theory, which is original setup.
But the number is not bounded. Could it be infinite?
Infinite where? It's string theory is the largest extra dimension
Taking
consider.
the limit n approaches infinity.
Take it. But if you take it infinity here, the radius will be 0. So there is no compactification. This is trivial observation, but I am saying that the more important, can I take it 1? No. Can I take it 2 with this limit? And in fact, if we probe gravity less than this limit and is not allowed to see it at this limit, we have to go to 3 and so on. Once you go to higher dimensions, up to 10, for example, you are close to the string setup, which give you very small radius of compactification, which is Planck length. Remember, beside this large or small radius, 2 or more, we have an assumption that the particle physics, the matter fields are localized on the 4-dimension and hyper surface that we call it brain. Okay, how it is localized, why it is localized. So far, it is localized. Yes.
Maybe a stupid question.
لا اسال ما فيش stupid question. Yes.
What are these dimensions? We know the 4 dimension, 3 of them special dimensions, and the 4th is time dimension. What are these extra
No time.
dimensions?
Time is complicated to say I have more than one time. That could be another extra. Imagine that you are, not you. في some object نملة عايشة على الحيطة دي. كويس؟ شايفه الحيطه ايه؟ 2 دي. تيجي تحلف لها بالايمانات المهم ان في دايمنشن هنا كده اسمه ثيرد دايمنشن انت مش شايفاه عشان انت ملزوقه في الحيطه، مش هتصدقها. انت كده دلوقتي انت مش مصدق ان في دايمنشن.
بس هي احنا حتى
هنثبته ازاي دي قصه ثانيه هنتفق عليها.
بس انا بتكلم على ماهيه
سبيس
الدايمنشن
سبيس spherical space. I'm extending the space 1 time plus 4 عشان كده all the equation 1 time بنتفاضل بالنسبه له بنحسب all evolution بالنسبه ل 1 time and instead of 3 4 space 4 space. Okay. Now this is interesting to the people ask about how we can prove these things. Well, we can prove from the graviton, for example. Graviton, we know it is massless field. It has an interaction with a gravity very, very small, suppressed with Planck scale, all this. However, now in this theory, Planck scale is not suppressed. We have M star, which could be TV. So the coupling is not huge, is not suppressed as before. Second, we have massive particle. We call it Kaluza-Klein excitation of the graviton. And in fact, the Kaluza-Klein excitation of the graviton, who was similar to the graviton, is coupled with all matter field. So in LHC or in ILC or whatever colliders, we could have process like proton-proton or electron-positron. You can have produce Kaluza-Klein with this is energetic. You need energy because this is heavy mass essentially. And then once you produce it, can decay to E plus E minus. Or there's a difference between these two blocks. So this is a way to produce kind of we have a photon, for example, mediates this interaction. You could have also another heavy particles, and then people in the LHC they are working to see if any peak or any invariant mass of the outgoing particle to show that there is a peak around the mass of the Kaluza-Klein. This is what they do, in fact, and I can show you the plots, but I don't have it here. But anyway, this is the way how they try to find out the Kaluza-Klein excitation of graviton at the LHC. Also, the Kaluza-Klein excitations could be stable and could play the role of dark matter, or could be long-lived, depends on it, because it has a gravitational coupling. So it could be long-lived, much more realistic than stable, because gravity is small, but is still you can decay. So here decay to E plus E minus, but with very small coupling, and therefore it could be kind of long-lived. So this is one particle of possible long-lived candidates that you may check. We go now to another setup. This setup, we said this is 4 dimension, this is the 5th dimension, and this is another 4 dimension other side, and this is our universe, and this is fine. This could be large extra dimension, provided that the whole volume is given large volume, so will suppress the Planck, and this is the story that I mentioned. Now we go to another setup which is called warped extra dimension. In fact, warped extra dimension is to take the same metric of the 4th dimension or the 5th dimension that here we decompose it, 4 plus the 5th dimension. But now the 4th extra dimension, G nu, 4 dimension metric, it has a factor f of y, because Lorentz invariance is require G mu nu dx nu. You can multiply this by any function which does not depend on the coordinates x and u. It could be function of y, because y is a 5th component, and the f of y looks like scalar function. And if you take f of y exponential mod constant times mod of y, this is decaying when you go from y equals 0 this point to y equals some value. You will find that will take this coefficient down to 0. So it gives you something like this. Here is a brane where we are living in 4 dimension, Here is y equals 0, so here is will be gr as normal because f of y equal 1, f of 0 equal 1 due to this expression. And this will be just normal gr. Once you go out from the brain, y is different from 0, y is large, it goes to takes this to be very small factors, and then it makes the gravity die outside. Only gravity die outside because all interaction are localized on the brain, as we said. This setup is called warped extra dimension because it is ds squared in 5 dimension. It has dy squared, the 5th dimension, and this is the 4th dimension multiplied by e to minus k times y. So this is known as warped extra dimension, and the theory is known by the name of Lisa Randall and Sondrom. What is his name? Something Sondrom. First name? Anyway, Randall Sondrom. First name I forgot. Anyway, Indian guy. So the hierarchy problem in this also is solved in a nice way, but it didn't work at the end because, in fact, the idea is to have your brain has blank scale which is really small, TV scale, and you keep blank, large blank scale at the second brain, at the faraway brain, and in this case you are happy, gravity is localized, interaction is localized, gravity is warped and dying in the, and also the blank scale is low in your brain. However, it doesn't work like this because when they studied this, they found the tension of this brain is really negative tension. This means that this brain is de Sitter space, not a Adil. When we solve the Einstein gravity, you will see there is a different solution depending on the sign of the curvature. So this is de Sitter, which is different from our space, which is either Minkowski or anti-de Sitter. We needed either de Sitter or Minkowski. So unfortunately, it doesn't work. Although the blank is really given in terms of some suppression factors, and the blank could be small, but unfortunately it could be small here on the brain, which is in the head sector. We wanted here, but here the brain not positive, not de Sitter, but anti-de Sitter, so we must to leave here. For that reason, they were not satisfied, and at the end of the day, they said, okay, this scenario and this extra dimension with warped geometry is perfect to say that the extra dimension is no longer needed to be compactified. It can be infinite. Take this extra dimension, take this brain very far away or throw it away, and then you have just a 4 dimension and the infinite extra dimensions that does not affect your brain at all. This is for the hierarchy problems, and this is Randall syndrome 1 when we have 2 brains, and we were hoping to have, this is hidden brain with blank scale 10 to 19, and this is hierarchy will be solved there because we have TV. However, unfortunately, this is ADS or anti-de Sitter, and this is de Sitter, and we must to leave in de Sitter. Therefore, this was not solving the hierarchy, and we end up with the model that I told you, this one. We take the second brain away, and we have just one brain and one infinite extra dimensions, and the situation is normal, and they give example for possible extra dimension with infinite large dimension. This is called Randall syndrome 2. This is again Randall syndrome 1 when they studied the cross-section of E plus, E minus, E plus, E minus. If any Kaluza line excitations mediate this process, you can see this peaks around the invariant masses, square root S, and this is could be telling you that there is Kaluza line excitation of order 800 or 200 2 TV mass. So this is a way how to measure excitations at the LHC, for example. Under Sondel 2, I told you that forget about the hierarchy, forget about second brain, just stay in one brain with infinite dimension, extra dimension. Planck mass is high, you have a problem of hierarchy, the matter is localized in the brain, and the gravity is warped, so that is not affected by very large extra dimension. This is excitation in the Randall Sondel 2. The same story, the coupling here is really could be of order 10 to minus 2 to 10 to minus 1. So large coupling and the Kaluza-Klein excitation can be effective in the process that you are measuring. The famous example in the LHC that the graviton goes to gamma-gamma or lepton plus lepton minus. So in gamma-gamma, you have quark anti-quark. It's producing kind of Kaluza-Klein excitation of the graviton, and then graviton goes to gamma-gamma, or gluon coupled to G, and G goes to gamma-gamma. And this is interesting process because it has almost a free background, and the people are trying to probe Kaluza-Klein through this process. Here again the result of the invariant mass of M gamma-gamma at some different values of the masses of the graviton. When I say graviton mass means Kaluza-Klein, first excited states. M graviton 750, 1 TeV, 1. So all this give you this kind of results. So a lot of work at LHC and the groups in Exotica groups to try to find out this.
So what is the physical scale involved in this of the compactification?
The Randall Sondel, it's a large scale.
How much? I mean, how?
No, you can take it infinite large because it's not affecting you at all. We remember the story. It's affecting you if you have if you don't have warped geometry. With warped geometry, you are free.
But you have a scale for the anti-setter length radius, right?
This is what makes a coupling. Kappa over M blank, or this is the coupling that you started with. To have a larger coupling, so you need kappa.
So the coupling is related to the radius of anti-setter?
And radius of
Anti-setter. You have an anti-setter space, right?
kappa, essentially it was appearing in this coefficient which
I think maybe this is a scale Amro is asking about.
yeah, but it is related to the orbit factor now because
Right,
the kappa
right.
mod y,
Exactly.
the kappa, this is the one which you fix the blank scale to be TV scale in the other direction. Yes,
So the question is the
Yes.
is related. Is
Yes,
related.
Yeah.
But it's not length of the extra
No, no,
dimension.
it's not.
It's the coefficient of the orbit factor. Because you need to have the orbit factor, you could have K very large, so the orbit factor will die immediately. So we found to get TV from blank, you need kappa times the R, the radius which you provide, of order some values. So they take it as your guidance for the coupling. Kappa over M blank star or bar.
Yeah, but that's an energy scale, right?
Yes.
So it's
Yes.
related to a length scale.
Yes.
So it would relate, for example, it would modify things like gamma rays traveling at very high energy and probing very small scales. Gamma rays from gamma ray bursts.
Okay, which is a scale? I am
And
confused.
very high energy gamma rays can probe very small scales on their way to,
Okay.
from a gamma ray burst to
Okay,
Earth.
what I want
So
to
there
say,
would be deviations and
right?
there are different dispersion relations than a normal.
I agree, but I want to say now you have two scenarios: either small scale from extra dimension like ADD or the usual Kaluza-Klein.
I'm a
This
bit
is a
confused.
this is a small scale that you are saying. Maybe I can probe it by high energy scale gamma rays or whatever.
Or other things.
But
yes.
now if you have very large
Yeah,
extra
this is
dimension-
very large. So what is this? I'm
yeah,
confused.
the factors which warp, which you taking gravity down to the zero, this is kappa. This is now is the one you are really adjusted to be in. If you have some result, then we are saying that kappa should be of that order.
But it also translates into some energy on land scale, or it doesn't. I don't
It's-
know.
It's translate,
I mean, the whole idea is
but not the size of extra dimension.
No, no, it's not the same.
It's not the size.
Yeah, but it could have effects on dispersion relations.
Yes, because it affects the warp factor go down quickly or not, or flat or whatever
Yes.
from this factor.
And other things. Like,
Yes.
For example,
Because in both
the
cases,
inflation
you use
modes.
an additional
Inflation.
Yeah, in the modes of inflation, for example, if they
Yeah, it will
if
affect
they
them
start
too.
on very high energy scales,
Right.
and there would be different dispersion relations,
I think so.
for example.
I think so. So this is gamma gamma that I mentioned. This is the peaks of the Kaluza-Klein excitation of the graviton at LHC, and this is now the experimental signatures. If you have proton-proton goes to Kaluza-Klein excitation, and then L plus L minus or gamma gamma. This type of plots is famous plots at LHC, and they have some predictions, but so far this is not yet giving more than few sigma, which is fluctuation. You cannot claim that we discovered some Kaluza-Klein, but this should be worked and improved more. Sharif and his colleague here, you can ask him if there's any chance to improve this to be, to have a discovery, you need 5 sigma. Here I think 2 point something sigma or so. So this is the story, and here is the summary of this example of extra dimensions. I don't know who was the best example to use for extra dimension, or it is more gravity than particle physics, but it solves the hierarchical problems. It relates things to the standard model as well, as I said. So this is an elegant solution for the hierarchical problem. Kaluza-Klein excitation of the graviton could be the opportunity to discover or to check these models from the resonant signatures at LHC. In fact, the current data, strong constrained random sodium parameters, no evidence for narrow resonance. I told you we need 5 sigma, so far is not that much. Up to 95% random sodium graviton mass below 545 can be excluded if the coupling is 0.02. If you reduce the coupling to 0.1, so this is small 2%. If it is 10%, then the constraint will be larger, of course. It will be 9, because usually you small coupling, you small the mass. You enlarge the coupling, you make the constraint of the mass much larger. Hopefully, in the high luminosity LHC, something will happen. We will have more sensitivity, and let us pray that Kaluza-Klein excitation of the graviton can be seen, so that we can prove extra dimension, and to convince you that there is extra dimensions. Is not just Kaluza-Klein excitation since the 30s. The situation is changing now. Okay, thank you very much.
Thanks, Shaaban. Any questions?
I have a question about the nature of the higher modes of the photons and gravitons. If they have masses, what about their speeds? They still move at the speed of light?
No. Speed of light only for massless particle. Speed of light is only for massless particle. Here they have mass, so the speed will be related to their mass, and it depends on the problem. So, for example, you have the energy that you produce. For example, this one, you have to do it like any problem in particle physics. You have to see the energy of this quark, anti-quark, or gluon, and then this will be like S. This is what is a channel, and you have momentum with mass and energy, and you calculate normal cross section as normal massive particle.
Are they still particle carrier for long range forces?
It's not that long range, not like the graviton, but yes, it is carrying kind of interactions, it is gravitational interaction because they are from the family of the graviton. The coupling is related to the Planck and the Newton coupling constant, so they are gravitational effects, but not long range as a graviton. They are massive, they are short range, they are having small coupling, so everything is calculated according to the scenario that you are assuming. Okay? Please.
We know that you told us that the graviton has a mass of anything above has a mass, it will be like short range interaction. So in 5 dimension, high dimension, gravity is short range interaction, yes?
هزعل. In 5 dimension gravity, we have gravity with the zero mode graviton, which is still long range force, and the other interactions like this. This is an excitation, which is massive, and you see it's very short. It's produced and then it decay. So it is short because it decay. This is gravity. This is an excited higher mode of the graviton.
So also electromagnetic will be like this.
Exactly. Electromagnetic will have the photon and the higher mode of the photon. They are massive and they will also produce and decay.
So the photon will be has a mass, has a speed less than c.
What?
This is
So
not
the
the
photon in
this
this
is not
the excitation modes.
If it is massive, then the velocity less than c. Yes.
دكتور هو عشان كده الجرافيتون يعني هما they assume ان هما بتوع المالتي يونيفرس وكده انه الجرافيتون هو اللي بيبحر ما بينهم هو بيسافر
بيبحر
بيسافر
There's no multiverses. Not directly.
هو ده كله هو ده كله في برينز وفي حيطه يمين وحيطه بس ده كله وان يونيفرس نوت مالتي يونيفرس. ممكن يبقى عندك مالتي يونيفرس في مالتي اكس دايمنشنز وتبقى كومبليكيشن بس ده اه in general
السنة الجاية السنة
الجرافيك
الجاية انت بتحضر لنا مالتيفيرس معاك.
in general الجرافيك والجرافيتون as you said هو اللي كان propagate in the bulk. نعم.
البعد الخارجي بالنسبه للعامه
ايه؟
البعد الخارجي
اه
بالنسبه للعامه حقيقي يعني دي